Good evening, everyone. Today, our team Dibya, Saurabh, and myself Swagato, we will be presenting on a configurable signal processing and DSP hardware generator for 5G and beyond transmitters. This work addresses a critical bottleneck in modern wireless communication, the rigidity of hardwares. Our presentation is based on research published in IEEE Transactions on VLSI systems, specifically focused on creating a universal, flexible hardware solution for next-gen transmitters. Here is our roadmap for the next few time. I'll kick things off by setting the context. Why 5G is so demanding and the different transmitter architectures we need to support. Then Dibya will take you inside the hardware itself, breaking down the filters and signal processing logic. Finally, Saurabh will explain our unique generator method and share the performance results from our 5 nanometer chip synthesis. Then, so why we need this? The transition to 5G and 6G brings two massive challenges. First, bandwidth. We are talking about multi-gigabit data rates that require massive signal bandwidths. Second, flexibility. Modern transmitters can't just do one thing, they need to support various complex modulation schemes. The problem is that designing a fixed hardware chip for each specific standard is incredibly expensive and inefficient. We need a single hardware design that can adapt or reconfigure to handle all of them. That is the problem we are solving. Then, to understand the solution, we first need to look at the architecture we are supporting. On the left, you see the Cartesian architecture. This is the standard approach used in phase 1 and quadrature Q signals. It's simple, but it struggles with efficiency at higher frequencies because analog components are not perfectly linear. On the right is the polar architecture. This converts those IQ signals into amplitude and phases. This is much more efficient for the transmitter, but it comes at a cost. It requires very complex mathematical operations to rotate the coordinates. Our hardware needs to handle both. Then we also go a step further to support outphasing. This technique splits the signal in two constant envelope vectors. This is brilliant because it allows the power amplifiers to run at full saturation, their most efficient state. Crucially, our design supports multi-level outphasing. Instead of just two vectors, we use discrete amplitude levels to scale the sum. This reduces the stress on the phase bandwidth and boosts the overall system efficiency even higher. Now, to explain how we built the hardware to do all this, I will hand it over to Dibya, my friend.
Thank you. Let's deep dive into the hardware architecture. The DSP unit you see here sit right in the middle between the digital baseband generator and the analog RF component. It has three main jobs. The interpolation chain that will upsample the data, the signal component separator which perform the complex math that Swagato just mentioned, and a clock divider circuit to keep everything synchronized. As you know the need of synchronization. So let's see what interpolation chain is. So when we convert signal to polar or outphasing, the bandwidth expands to like 5 or 10 times. So to stop the signal from distorting, what we do is we upsample it significantly. So we use a chain of 3 half band filters. We choose half band filter for a specific reason, that is efficiency, because nearly half of the coefficients will be 0. This means we can perform high quality filtering with 60 dB attenuation while using a very few multiplier which saves power. Now let's move to high speed CIC filter. So For this final massive jump in this sampling rate up to 128 times the original, we use a cascaded integrator cum CIC filter. This filter is special because it multiplier free, which required which is in analog domain. So it only uses only adder and delays. However, running this at our target speed of 4 GHz very hard. So to fix this, we unroll the loop. Instead of processing one sample at a time, our hardware processor process 4 samples parallelly every clock cycle. This let us hit high speed without needing exotic and expensive transistor. So next, let's move next to the signal component separator, which is the brain of the modulation actually, the whole operation. So this modulator takes standard IQ data, that I phase and Q phase data, and mathematically transform into the theta for out phasing or amplitude / phase for the polar. It uses the coding algorithm. Specifically for out phasing, we implement a specialized double iteration algorithm. This allows us to create the inverse cosine very accurately using about 15 iterations without running into scaling error. So finally, I want to highlight about the strategy of speed using the time interleaving. Doing complex codic math at 4 GHz is extremely difficult. This logic simply can't switch the fast without overheating. Our solution is time interleaving. We run 4 parallel instances of SCS at a comfortable 1 GHz. SCS, as I said you, this signal component separator. So we multiplex or combine their output to achieve the final 4 GHz rate. This gives us the best of both worlds, high throughput with manageable clock speed. So I will now pass to Mr. Saurabh Sarkar to discuss our results. Thank you.
Thank you, Dibya. Let's move on to the final part. Now, I want to talk about how actually we built this. We did not just design one chip. Actually, here I am mentioning to the paper's author, they built a generator using the SDK framework and the Chisel programming language, and they created a parametric design. This means that by changing the single line of configuration code, same code base can be automatically generated on a Cartesian chip, a polar chip, and even on an out-phasing chip. It is correct by construction and extremely flexible. So, does it work? This paper has shown us that they have tested the generator hardware with a wideband 6G and 5G signal. The table here shows the results. The multi-level out-phasing mode, which is most advanced, achieved the best performance with an error vector magnitude of just 0.78% and a very low noise leakage. These numbers prove that this automated generator produces hardware that rivals even the handcrafted designs because of obvious reasons, which is automatic. Now let's move on to the synthesis part. They have synthesized this design using an advanced 5 nanometer CMOS process. One key optimization they made was in the number formatting. They have used a fixed point format called Q1.14. By carefully turning the number of bits, we reduced the switching activity inside the chip by 10%. As we all know, in the real world of chip design, less switching directly equals to less power consumption of the less heat. Now, to really show the impact, we compared this work with the previous design built on 22 nanometer technology. The difference is actually night and day. The paper says that they have reduced the power consumption from 142 milliwatt down to just 37.2 milliwatt. That is a whopping 73% reduction. At the same time, the core idea of the chip shrank by even 91%. This proves that our generator approach scales perfectly when you move to the newer and better technology nodes. And to conclude it all, we have presented a universal DSP hardware generator. It is flexible enough to support all major transmitter architectures. It is fast enough to run at 4 GHz, and it is efficient enough to enable the next generation of low power 5G and 6G radios. Thank you for your attention.